Welcome back to our journey through dynamic topology. Today we're going to do something really cool. We're going to take two concepts we've already gotten pretty good at and fuse them together to create something even more powerful. Let's get right into it.
First things first, let's do a quick refresher on the two fundamental tools that we've been using to describe shapes. So first up, we've got connectedness. This is our precise mathematical way of saying that a set is basically a single unbroken piece. It's the property of being whole. And then second, we have compactness. Now this is our tool for describing sets that are totally self-contained, totally complete. It's like they've got all their limit points locked inside. Nothing can escape or leak out.
Okay, so this leads to a really fascinating question, doesn't it? What happens when we demand that a set has both of these properties at the exact same time? What kind of beautifully constrained object do we end up creating?
Well, the answer to that question, it gives us one of the most important and useful objects in all of topology. It's called a continuum. A continuum is just the perfect fusion of these two ideas. It's a shape that is both a single, unbroken piece, and it's completely self-contained. What's really interesting here is how this clarifies the relationship. A continuum isn't some brand new out-of-the-blue idea. It actually inherits the essential nature of both of its parents, so to speak. It gets its one-piece-ness from being connected, and it gets that self-contained property from being compact. So the really crucial point is, why does creating this new category even matter? Why do we care? Well, it's because continua have some amazing and incredibly reliable properties. Honestly, you can really think of these properties as mathematical superpowers. They make continuums so stable and predictable, which means we can count on them to behave in certain ways even when we start manipulating them. And this right here, this just illustrates their robustness perfectly. No matter how you stretch or squash a continuum with a continuous function, it stays a continuum. If you merge two of them that touch, guess what? The result is still a continuum. This stability is the real aha moment. It's what allows topologists to prove these really deep theorems about incredibly complex shapes, because they know these core properties will always be preserved. All right, in the spirit of the why-burn method, let's not just read about these properties. Let's get our hands dirty. Let's prove one together just to see how it all works. So we're going to tackle this core theorem. Taking two continua that overlap and joining them together creates a brand new, larger continuum. And to prove this, all we have to do is check if our new shape still meets the two conditions for being a continuum. Okay, so we can break this proof into two really simple checks. First up, connectedness. We already know from a previous theorem that if you join two connected sets that touch, the result is always going to be a connected set. So our new shape passes the first test. It's connected, check. Second, compactness. A really key theorem states that the union of any finite number of compact sets is always compact. And since we're only joining two, our shape passes the second test. It's compact. Check. And because our new set satisfies both of those conditions, the proof is complete. It's really as simple as that. So we've now defined what a continuum is, and we've even seen its power in action. This now opens the door to an even deeper and frankly more fascinating question for our next session. This is the whole concept of an irreducible continuum. It's this beautiful idea about finding the most efficient topological path possible within these structures. And that's exactly where our exploration is headed next. Thanks for joining this explainer, and I will see you then.